Thank you very much for the invitation. I was putting off reviewing some of the newer data because it's so labor intensive, but now I'm glad that I did. There's a lot of things to learn. Since the early 1990s, this concept of system balance has been important to me. I've been trying to follow it as quantitatively as possible. Today I'm going to talk about two topics. One is the changes in the systems on the top 500 lists. This is a proxy for the high end of HPC systems. I'm going to talk a little bit about technology trends and how they lead to changes in system balances with regard to both latency and bandwidth. So let me just jump right in. Top 500, what is it? If you don't know, the top 500 list is a list maintained by Jack Dennard at the University of Tennessee and his colleagues. It's a list of the 500 fastest submissions that they have received for performance on the high performance LinPack benchmark, which is a solution of a dense system of linear equations of arbitrary size. Of course, the list only contains systems that are reported. Some sites, such as the Blue Waters system at NCSA, which would have been very high on the list, chose not to submit that benchmark. There are also reported to be secret government systems, which don't have reported results. There is a fair amount of, let's call it, gamesmanship on the top 500 list. The benchmark does not actually need to be run on every system that's submitted. It only needs to be run on one instance of any particular configuration. And the system doesn't need to be used for HPC. In the early 2000s, there were certainly a lot of commercial systems database clusters. I got a bonus one year when I was working for IBM for producing performance models that would allow IBM to figure out which system configurations should be submitted to the list because they could probably make it onto the bottom of the list. Recently, there are a large number of entries on the list that are pretty clearly web services, cloud systems that don't have anything to do with HPC. But the high end of the list is overwhelmingly dominated by systems that are used for HPC, and that's where a lot of my attention will be. An issue that can affect how you interpret the results is that the customers, or including the vendors, choose how to submit their results. And for depending on how you want to count, you might want one big system or several smaller systems. If it's going to be on the top of the list, most people choose a big system. But if it's not going to be too close to the top and you think you can split it in half or get two, that's how a vendor's going to do it. If you have heterogeneous clusters, it will depend on your software. For example, the TAC Stampede 2 system has 4,200 Knights landing nodes and 1,736 Skylake Xeon nodes. And the only reason we were able to submit a single result is that Intel did the software development to provide an application, a binary that would run the HPL benchmark on that heterogeneous system. So there are some software availability issues too. So what comes out of the top 500 list that I'm going to analyze? There's a database you can download from the top 500 website, an XML file for each list. I did that. It looks nice. The only problem is that there's no system configuration data. So that leaves me downloading the Excel files, and I just started redoing this again recently. There are 58 top 500 list. It's presented every 6 months since June of 1993. Across those 58 lists, there's actually 15 different formats in terms of combinations of column headers. There's also a lot of information. There's minimal information about system configurations, which can therefore sometimes be misleading and it's sometimes wrong. So I've spent hundreds of hours in aggregate fixing errors, looking up system parameters and reverse engineering configurations. I'm working on trying to make that a little bit more systematic now. I've gotten to the point where I can press a button and have all of the original Excel file data collated into a single, essentially column separated value table format with all the headings normalized and everything in the correct column. Next comes transferring all of the work I've done on fixing mistakes and reverse engineering system configurations, which is going to take a while. So the top 500 list reports a couple of things, but the one I'm going to start with is Rmax. Rmax is the performance seen on the solution of the system of linear equations. For each list, I add up the Rmax, essentially the gigaflops delivered by all of the systems on the list, and then I assign the I split it up by system architecture. Now, what do I mean by that? In the early lists in the 1990s, they were dominated by the traditional vector machines. These were the Cray XMP, the Cray 2, and follow-ons, the NEC SX4, some Fujitsu vector machines. The next large category that I look at is clusters based on, well, not just clusters, but clusters or SMPs based on RISC microprocessors. This includes a very large number of different processors, especially during the 1990s. Intel i860, it was the DEC Alpha, MIPS processor, Spark processors, IBM Power, and others. Those completely dominated the lists from the late 1990s through 2004, 3 or 4, thereabouts. The next large domination of the list came from x86 processors, a combination of AMD and Intel. In the early days, these were mostly 32-bit, but by 2005 or so, almost all of them had been shifted over to the 64-bit extensions, the x86 architecture. There's another category that is probably closest to what the top 500 list calls MPP. For this talk, I'm going to keep that label, but also I'm going to call it specialized systems. And what I'm trying to get across here is that these systems, the most expensive part of the system development, which is usually a processor, is expected to be paid for by either direct government funding or by only HPC type customers. The vector machines, of course, are in the same category. Those were almost exclusively used for scientific computing. But the RISC processors and x86 processors were able to pay for their processor development by selling to much larger markets. So I track these sort of specialized MPP systems separately. And then finally, the newest category is accelerated systems, which in this case are standard microprocessors, either x86 or IBM Power, with add-on accelerators for offloading certain computations. I want to make sure everybody remembers that the top 500 list has a system architecture category included in the database. These are my categories, not the top 500 categories. And there are some places that they're significantly different. I'll mention some of them as we go through this. I should say a portion of the accelerated system performance actually does come from the microprocessors, either x86 or Power. It's not included here because it's not easy to separate that. A new number one system on the list often makes a pretty big impact on the distribution. And I've marked some of the places where one of the categories gets much bigger. In 1997, for example, the ASCII Red machine, which was a 32-bit Intel processor system, introduced the first significant x86. The Earth simulator was a big peak in the vector machines. IBM Blue Gene machine, which I count as a specialized system, in around 2006. Roadrunner was the first very large accelerated system. It had AMD Opteron processors and IBM Cell accelerators. Tianhe 1A, another large accelerated system. Tianhe 2, even bigger accelerated system. Taihu Lite I got in the category of specialized systems. It is also accelerated in its programming model, but well. Summit is IBM Power with NVIDIA GPUs as co-processors. Finally, Fugaku, which is perhaps the most controversial of my classifications. I list it under MPPs, even though these are, in some sense, standard ISA ARM processors. Before this talk, I went back and reviewed the history of Fujitsu's sales in HPC and commercial markets, and I would love it if these become more popular and end up getting paid for by a larger market. But my feeling right now is that they were almost certainly paid for primarily by government funding, and that really is probably not going to be recouped into the broader market. So I left it in the MPP category. One of the things that happens as we change these systems is huge increases in the required thread concurrency to use a top 10 class system. So in the early days, in the early days, the vector machines might use as few as 4 vector cores. And then, slightly larger, 1632. Our simulator did kick that up significantly later on, but those were numbers that were pretty easy for an individual to deal with. With the RISC systems, the high-end machines started off in hundreds of processors, then a few thousand. With x86, they started with tens of thousands and gone up to hundreds of thousands. The specialized machines can require order millions to almost 10 million threads. And the accelerated machines require even larger thread counts. And I put question marks on this 100 million because there are so many different levels of parallelism inside, for example, an NVIDIA processor. There may be, I count, the top 500 list counts processors, or processor cores. And for CPUs, a processor core is relatively easy to define. For GPUs, it's significantly harder to define unambiguously, I guess. And my convention that I've been using for NVIDIA processors is SMs, or their own internal blocks, but an SM may have 64 little cores inside of it, so that takes the millions up at least to tens of millions. Of course, what's driving the increase in processor counts, thread concurrency required, is a decrease in the price per processor over time. This is my personal estimate based on kind of watching things for a long time. In the olden days, a vector machine was $1.5 million a processor, maybe coming down to $1 million for the larger machines. The RISC processors tended to be in the $50,000 range, and then dropping a little bit to maybe 25 by 2000. x86 processors have shown a different trend. If you count by socket, the price per socket started off dropping in the 2005 sort of time frame. I think it reached a minimum around 2007 or 2008 with dual core, maybe the quad cores. Then the price per socket has been going up slowly but steadily over the last 10 years or so. If you try to calculate the dollars per core, the dollars per core is clearly going down. What this leads to, and I was thinking about this in terms of when I started as an assistant professor in oceanography 30 years ago, I had a startup budget of $50,000. And since I was a numerical modeling professor, I used some of that money to purchase computers. Back then, that allowed me, that was 1990, that allowed me to purchase one core that I could buy for my, it's not exactly true, I had two, but that's pretty close. With the multi-core and the shift to x86, this is going up, and it's going up to really pretty crazy numbers. I had little trouble keeping one compute node busy the whole time, running, long runs, setting up a queue. It's not too hard to keep 10 cores busy, especially, or 100 cores. That's starting to get really hard, even running threaded applications. Now that same budget buys you 500 or so cores, and it changes how you use the systems. It changes the programming models that are required. It changes how you think about sharing them. A peculiar thing about the industry is that in the 1980s, there were no available computers that did number crunching at lower prices. That's not exactly true, but they weren't very good. The most cost-effective systems were actually these big vector machines. So all the money in the institution went to buy these big machines, and then they were shared by the users. When the RISC processors came out, they were now available in price ranges that individual departments and then investigators could buy. And so the money was split into different buckets that were shared then less widely. And the same with x86, now it came down to every graduate student has their own computer. One of the consequences, I believe, of these increasing core counts is that it's pretty easy for me to maintain as an administrator one system, my personal workstation. If that became 16 systems, that would really not be very pleasant. And I think I would lose a lot of my work efficiency in administering those machines. So there's actually been a shift toward larger institutional systems which are shared and for which the administrative budget can be shared and the systems can be run more efficiently. This in combination with some sort of political factors has led to some significant changes in the distribution of systems of performance in the systems on the top 500 list. This is a sort of a funny chart that looks at the performance at different ranks relative to the #1 system on the list, starting in 5-year chunks. And what we see is, with some noise, definite shift toward much lower performance, much higher performance, a much higher fraction of the list's performances in the top couple of machines. Partly that's politics. Countries have realized the sort of PR value of these large machines and are investing large amounts of money in them. But that ratio actually continues down the list. Another way to look at this is the fraction of the total list performance contained in the #1 machine. It was quite steady here. The Earth simulator was the first time that it jumped up over about 8%, jumped all the way up to 16%. And it's sort of steady again at a slightly higher level, and then jumps again here in 2012 to a much higher average level. If I look at the top 10 systems, which have top 10 is a pretty easy advertising number, we see again stable the 20 to 25% until our simulator, and then sort of coming up again, and then this huge jump here with Tianhe 2. 48% of the aggregate performance of the top 500 list was in the top 10 machines in 2013, 14. And it seems to now have settled at a new expectation value of roughly twice what it was before. So this is a very top-heavy list. Now I want to shift and talk a little bit about some of the technology trends that are responsible for these changes and balances. So what do I mean by balance? I view performance as an n-dimensional vector of these mostly orthogonal components. So there's the arithmetic computation rate. There's the rate at which one can transfer data to and from memory. There's the latency for those individual memory transfers. Now that all the systems are clusters of some sort, there's interconnect bandwidths, interconnect latencies. And the system balances or ratios of these components. I typically write them in terms of flops for one of the measures, and see how many, for example, with memory bandwidth, how many flops can you do in the time required to transfer one word of bandwidth, one word from main memory out of a large stream? So looking at those individual components, the peak flops are continuing to rise at very high rates. The bandwidth is increasing at a lesser but still very solid rate. Memory latency is typically increasing, which is the wrong direction to go. This is, I think I have another slide on that in a minute. Interconnect bandwidth is going up at a modest rate. Interconnect latency is going down at a modest rate. And so the combination of these things suggests that processors will be increasingly imbalanced with respect to anything that involves data motion. And I apologize here that I didn't get a chance to split this out into multiple separate charts that we could talk at one at a time. I'm going to start from the bottom. This balance, the way I typically define the stream balance is in peak floating point operations per second divided by sustained words per second of memory bandwidth. In the early 1990s, so the systems that I chose for this chart are subjectively chosen. I picked systems that were good and they were commercially successful and they were considered to be well balanced at the time that they were being sold. And I can get you the list of those later if you need it. In the early days, this was an IBM Power 1 processor. You could do about 5 or 6 floating point operations in the time required to transfer one word from to or from main memory. And that began increasing. People increased cache sizes as an attempt to compensate, but remember, these are the good machines. They're at any one time there are machines for which the bandwidth is dramatically factor of 10 or more lower. But even among the good machines, by the time you get into the 2000 range, floating point operations are now costing 25 or 30 floating point operations could be done during a memory transfer. By 2015, that roughly hit 100, and now we're looking at for the bottom is a AMD EPYC Milan processor. The top one of these squares is a Ice Lake Xeon processor, and they're both in the range of 100 to 200 floating point operations per word transferred from main memory. This is what the stream benchmark measures, and this is what I started working on, this sort of the topic of the memory wall. But that is the best of the trends. They skipped to the local memory latency trend. Latency, because clocks used to be slower, latency wasn't that much worse. You could do some tens of operations per memory latency, and then it became hundreds, and then it became thousands. Now we're at 5,000 to 6,000 floating point operations for local memory latency that's not overlapped. Interconnect bandwidth is showing similar trends. Interconnect latency is showing the worst values on this chart. Now, this is all presented in terms of the floating point operation rate for one core. So these values are, if one core has to wait for an interconnect latency, how many floating point operations could it have done during that period? And it's 50 to 100,000. This again is the Ice Lake Xeon, and this is the AMD Milan And I should say that the reason that this ratio, the Milan, has a lower number is because its peak performance is lower, not because there's anything better about its interconnect latency. As we move toward more complex machines and more complex programming models, it may not be a single core that's stalling on a local memory. It's quite possible for the entire package to stall on a local memory access. An easy example of this is an OpenMP code in which the primary thread, the controlling thread, takes a stall while all of the working threads are waiting for work to be given to them. So this is for a single core, this is a repeat, the lower line. And the upper line shows that we're now in the range of 200 to 300,000 floating point operations per core, and for floating point operations per chip per local memory latency. And of course, it gets worse for remote latencies. This is the same as before, the single core waiting on a interconnect latency. And now here is the entire package waiting on interconnect latency. This is very easy to do if you have an MPI code that is waiting on collective operation, for example. And it doesn't, it could be a hybrid code in which the worker threads are all idling, but it doesn't have to be. Even if you're running one MPI rank per core, the collectives are blocking in some respects. So this is the sort of cost. It's pretty amazing that in the mid 1990s, it only cost you 200 flops to stall for an interconnect latency, and now it's 2 million. That changes things pretty substantially. So going under to the technological roots of the problem, why are flops increasing so fast? The peak flops per package is a frequency, sort of a width, floating point operations per cycle per core, which depends on how many floating point units, how wide they are, what kind of instructions you have, and then the number of cores per package. In my 2016 talk, this is the slide from my 2016 talk, and I left it in here because it's got better annotations. What I'm showing here is the base 10 log of the gigaflops contribution to the peak flops per package. And so that 1 gigaflops here, and I've divided it into a frequency of cores, frequency of cores, and width or floating point operations per cycle. We started off with Pentium 4s, high frequency, 2 floating point operations per cycle. At core 2, frequencies are kind of the same. We now, oops, that should be a 4. 4 floating point operations per cycle. Nehalem Westmere brought it up to minimal changes in frequency, same floating point operations per cycle, but more cores. Sandy Bridge, Ivy Bridge doubled that. Haswell and Broadwell doubled the floating point operations per cycle again and increased the cores. And now you see a significant reduction in frequency, and this is power limited by just the semiconductor active power. In 2016, the Skylake was a projection. I have it hashed out. We've doubled the flops per cycle again, increase the number of cores again, and drop the frequency some more. And putting on sort of the newer values, what we see is a continuing reduction of frequency when all cores are active, and a continuing increase in the number of cores per socket. And for the moment, the number of floating point operations per cycle is roughly fixed. This is a the right-hand column is a projection for some product that might be delivered next year. Now, in excess of 1 teraflop peak per socket, and heading toward 10. But why is memory bandwidth increasing so slowly? There's been a pretty slow rate of pin speed improvement. Part of this is signaling. Part of this is DRAM. The emphasis in the DRAM market has always been on either increasing the capacity or reducing the cost for a fixed capacity. Bandwidth has not been considered economically important. People will pay for capacity. They tend to not want to pay for a higher transfer rate. The shared bus architecture used by most DIMM technology is extremely hard to scale to high frequencies. We already find that installing more than one DIMM per channel can cause the system to reduce its frequency. The fundamental problem is that the DRAM cell cycle time is really almost unchanged in 20 years. It's pretty much 60 nanoseconds for a full cycle of a DRAM cell to be read and recharged and ready to write a new value. Because the cycle time hasn't changed, the speed increases have required that you just transfer more stuff in parallel. And we're now up to a minimum of 64-byte transfers for DDR3 and DDR4. DDR5 has actually had to split the interface from 64 bits into two 32-bit interfaces now, which each have 64-byte transfers. Of course, the interface width is an issue because pins cost money, and nobody wants to pay more money for the DRAM chips, for the processor chips. Once you get to the point of having 8 DRAM channels attached to a processor chip, that is many hundreds of I/O pins, which puts it in a significantly more expensive category of package. But what's going on with memory latency? There are a couple of problems. One is that there's more levels in the cache hierarchy. There is some parallelism in the lookups, but you can't parallelize too much, or you lose the advantages of the extra levels. One of the problems, which I think is rather poorly appreciated, is that because of power restrictions, our chips have more and more clock domains that are independent. And you have to cross these clock domains. Crossing a clock domain requires a specialized interface that adds latency to the signal path. An example here of clock domain crossings on a 2-socket Intel-based processor. The core is at one frequency. It has to cross into the ring uncore frequency, which switches to the QPI frequency, which has to then match to the ring on the other chip, back to the QPI, to the ring, and to the core. Even going to local memory, the core talks to the uncore, which talks to the DDR, which is typically unsynced, and then back. The remote memory is worse. So a couple of cycles lost at each of these crossings will make it harder. Of course, we're also adding cores, and they have to stay coherent. This has gotten to the point where coherency is really very challenging. I've spent quite a bit of the last 3 years working on trying to understand what I think Intel has done wrong in their implementations of, I say that in a performance sense, not a functionality sense, and their implementation of cache coherency on their Xeon processors. What Intel has done is very impressive. They have, for each core, private L1 and L2 caches. They have a shared L3 cache, but that L3 cache is distributed into slices across the chip. Typically, slices are co-located with the cores. But once you miss in your L2 cache, the data is sent to one of the L3 slices somewhere around the chip. This would not be a very difficult thing to do if the number of cores was a power of 2, but they have to deal with core counts now from, say, 4 to 40 to 68 on some of their processors, including all of the prime factors up to 13, I think, maybe. I don't remember. I don't know if they do 17 or not. I think maybe they skip 17. But designing a hash function that distributes data across all of those different core counts effectively is very difficult, and there are some issues with the implementation. But it does provide a single processor with the appearance of a large single L3 cache. On two-socket systems, the latency is almost always dominated by the coherence response from the other socket, and that has led to the development of some additional filtering mechanisms. Intel processors, starting with Skylake, include directory information with the data in memory that can be used to decide whether or not you need to even ask the other chip. And there are also more hops required on the chip. We can't build on a chip, we can't build the high degree topologies, hypercubes, or whatever. These are typically two-dimensional meshes, and the hop count increases as the core count increases. Also, the frequencies are going down, at least for the cores. The uncores are about the same. The DDRs are going up very slowly. But the combination of these factors means that in that very complex optimizations need to be applied to provide even the appearance of reductions in latency, and those only sometimes work in special cases. Interconnect bandwidth. The pin speed improvements are not so bad. There's been a reluctance to increase the interface width. Switch chips are typically pin limited, so the wider interfaces would get fewer ports, which would mean more switches, and that provides a number of additional problems. The latency, my opinion is that the entire I/O architecture of modern machines was really designed. The architecture was specified back in the day when I/O meant disks, not communication. Control operations between processor and I/O devices use uncached loads and stores or interrupts. These are hundreds of cycles, thousands of cycles, and often have no concurrency. So it is there is an architecture that is not well suited for low latency communication and synchronization, which is now being used for high bandwidth interconnect processing. There also tends to be a mismatch between software requirements and hardware capabilities, but that is sort of getting into a larger topic that I don't really have time for today. Let me talk a little bit about latency, bandwidth, and concurrency. Little's law is the usual name given to this from queuing theory. It describes a relationship between latency or occupancy, bandwidth, and concurrency. It's very simple. The latency times the bandwidth is equal to the concurrency. The way I interpret this is the latency times the bandwidth is equal to the amount of data that has to be in flight on the channel in order to attain full bandwidth, in order to hide the latency. So if your latency is flat and the bandwidth is going up, you have to increase the concurrency. You have to increase the number of outstanding transactions in order to use that bandwidth. These are exponential trends, and so these can be very large changes. I had to go all the way back to 2005 to give an example of this for local memory accesses. In 2005, on an Opteron, we had a latency of about 60 nanoseconds. The DRAM transfer rate was 6.4 gigabytes per second, so 10 nanoseconds per line. 60 nanoseconds divided by 10 nanoseconds per line means you need 6 cache lines in flight to fill the memory. The direct calculation gives you 384 bytes, then I convert it to cache lines. And that gives a pretty simple signal. You put your request out every cycle, and once you got 6 of them out there, now you start receiving data, and you receive data on every cycle. The numbers now are not 6. This is some representative systems. What I'm plotting here is how many 64-byte transfers have to be in flight concurrently in order to fully tolerate the latency and use the full bandwidth. I've divided this up into a couple of categories. The squares are mainstream processors. The red circles are NVIDIA GPUs, got a couple of Intel mini cores in there. And we see this fairly significant trend going back starting around 2005 of 33% per year. The trend in the GPUs is a bit lower, maybe, but not much. These values are a bit terrifying. This is a Ice Lake Xeon 40 core, which needs to have 227 cache lines in flight to tolerate the memory latency. This is an NVIDIA Ampere A100, and that number is 2, 3, 4, 5, 6,500 or some ridiculous, something like that. This need for concurrency is, see, I thought about this on my next slide. Why is this a problem? For CPUs, architectures are built assuming a flat memory model. The location of the data in terms of which socket and which cache is invisible and uncontrollable. Caches and prefetchers are assumed to be good enough to cover the latency and bandwidth differences. And that actually worked really, really well when you only needed maybe 4 cache misses, 2 or 3 or 4 cache misses. All you had to do was reduce the miss rate a little bit with your larger cache or with some prefetching, and you were in great shape. Implementations only support a limited number of L1 data cache misses. 10 or 12 on recent Xeon processors. And remember, I said 227 per package on an Ice Lake Xeon. If a processor can only get 10 outstanding misses, that it's not going to get to that 227. The L2 hardware prefetchers help, but they are also not controllable. They get you up to typically 18 to 20 effective outstanding transfers per core. And again, that doesn't get you to 227 very fast. So lots of cores are needed just to generate enough concurrency, enough cache lines in flight, even if they're not needed to do the computing. This actually does cost quite a bit of energy. If you look at something like the stream benchmark with the bandwidth and arithmetic capability of current systems, I think that I could run the arithmetic for the stream benchmark on one core without any problem at all. But one core doesn't generate enough concurrency. So I have to power up all these other cores and have them all stall most of the time. Also, that concurrency adds a huge amount of cost for development and power and silicon area in order to handle these concurrent operations. The DRAM page management requires that you review all of the outstanding operations to see which ones fit into the open DRAM page. The buffers have to be bigger. Power goes up. Bandwidth utilization goes down. The development cost of the system becomes higher. And all of this is due to an architecture that was specified 30 odd years ago that assumed that all you needed to do was say load and everything would be taken care of from there, and prevents you from giving any more information to the system than just the address of the data item that you want. Increasing concurrency also hurts. More cores create more access streams, which to service would require more DRAM banks. We often see that in modern processors, reducing the number of cores in use will increase the sustained bandwidth by providing a better match to the available DRAM banks. For example, a chip that has 40 cores might deliver its best bandwidth using 16. Oh, here we go. An older example, I did an update. Each core is generating a couple of address streams of read and write back traffic. And so the more cores you have, now we're up to 40 cores with 2 streams each would be 80 banks, but there are only 16 or 32 banks on the system. So you run into trouble. Hyperthreading is a very common cause. We often on Intel type processors see a 3 to 5% performance bandwidth degradation if all of the streams are accessing memory. And adding more DIMMs to get more ranks may or may not help because the interface requires stalls when you're switching from one to the other. And my last topic here, there's a lot of talk about power and energy, and it's absolutely true that power density is very important in the implementation of the processor. It limits the frequencies. We've got cooling issues, and now we've had to invest a huge amount of money in these mechanisms to throttle the frequency. But power is not a first order concern, at least in the United States. In operating costs, what we find is that purchase prices are around $4,000 a socket. Socket draws more than this now. It was 100 to 150 before. It's a little higher. But at the prices we pay for electricity, the power required to run the system is only 5 to 7% of the purchase price per year. And this ratio is actually quite hard to change. Of course, you could make the power a lot more expensive, or you could make the processors a lot cheaper, or you can make the processor draw a lot more power. None of those things are easy to change. And if much cheaper processors were available, power could become a first order cost. And you'll see that with much cheaper processors like PC client processors. Really the similar architecture, but a much lower price. It's also possible with embedded processors. A $5 processor using 5 watts might take $7 a year for power. This isn't a problem for mobile. For HPC, it would be a very interesting sociological problem, because now your budget has a new kind of flexibility that you're not really prepared to deal with. You have the depreciation cost. You have to replace the system every 5 years. But now you have this variable cost associated with power use. And that's all I have time for today, and I think I timed it relatively well. Time for questions.
What is your all-time favorite HPC system / processor / architecture, and why?
Well, that's a hard one. For the kind of work that I was doing back when I was an academic, the vector machines, the Cray vector style machines were wonderful. They were too expensive, so they had to be shared, but they were very easy to use. They're very easy to get good performance on. Over time, there's usually been an implementation of processor type that has been, it's had a better feel than the others for its overall productivity. The DEC alpha processors in the microprocessor world were like that. The Opteron processors were like that. It's a combination of a couple of factors. One of them is having good bandwidth relative to the competition, and also not having too much floating point. It's easy for vendors to add additional floating point units that don't actually make anything any faster. And I think as a performance guy, that makes me cranky, because I want to try to figure out how to get that performance, but you just can't. So one of the characteristics of the best microprocessors in terms of this balance and this feel of efficiency is to have more load store units than you have arithmetic units, and that's actually quite rare. If you think about the basic operation that you might do, vector addition, that requires loading 2 vectors, doing a computation, and maybe storing a result. If you're accumulating it, then you don't need to store it till the end. But that's load 2 elements and do 1 add. What we find in almost all current processors is that there's only 1 load store unit for each arithmetic unit. So half of if you're doing this kind of work, half of your arithmetic capability is not useful. It's really only useful for convolutions or dense matrix algebra, where you can reuse items with register blocking. So one that I like right now is the NEC vector engine. It's an add-on PCIe card that uses the vector style model, but is affordable sort of by an individual. It's especially nice because due to the limited concurrency in microprocessors, the bandwidth available to a single core has been going up quite slowly. It's maybe 20 gigabytes per second on a good microprocessor right now. A relatively small fraction of the 200 that's available on the chips. And the NEC has nearly 1,000 gigabytes per second bandwidth, and you can get 300 out of a single thread of execution, so 15 times what I can get out of a microprocessor solution without parallelizing. And sometimes it's nice to not have to think about parallelization that early on in the process.
Okay, so I can only agree with what you say about the NEC vector machine. We have 2 of those cards in our test cluster, and it's really a marvel to work with. Okay, next question by Klaus Pankatz. What is the cause for the reappearance of the vector machines in recent times? I think he refers to the little red bit.
Yes, those are the NEC vector engines. Yes. In exactly. Like 1 or 2 large systems in Japan. I don't know whether they will make a large difference in the market, but they are, I think, quite helpful for reducing the amount of parallelism that I need to think about. I just need to arrange that my computations are vectorizable and let the system take care of that.
Okay, just as a side note, there's one big system outside of Japan. The German weather service in Offenbach has procured a big supercomputer system. All right, Steffen Christgau asks, about 10 years ago, we had prototype x86 processors that intentionally dropped support for cache coherence. I think he refers to the single chip cloud chip by Intel. Do you think there's a chance we will have processors in the future which have coherence islands, which is only local coherence, although technologies like CXL attempt to provide a coherent view on the system?
Yeah. This was a topic that I started paying attention to a while ago. 2006, 7, and 8, I was the technology lead for AMD's third-party accelerator program. It took the first year that I was there to actually convince myself that I/O on microprocessor-based systems was actually as stupid as it was. But yes, it is. The coherency was a topic that came up a lot with accelerators, and what became clear to me is that coherency is not the right question to ask. The way I usually describe it is that we have 2 kinds of data transfers in systems. We have vertical data transfers, which are transfers up and down the cache hierarchy, and the cache handles trying to keep frequently used data close. And we have horizontal transfers that are related to communication between cores or accelerators. Those require fundamentally different optimizations. In a vertical motion, if you store data, if you modify data and store it, you should keep it in the cache close to you because you may need to read it again or modify it again. Horizontal transfers, that's exactly the wrong thing to do. When I try to write to a memory location that you're polling on, I write to it and it stays in my cache. There's no architectural mechanism for me to send it to you. So there's a huge need, and this is a different talk. I would say that current architectures are fundamentally broken because they don't take into account the difference between vertical and horizontal data motion. So dropping support for cache coherence, yes, there's in a lot of programming models, you have a lot of private data, and all of it is kept coherent at a significant power cost, even though no other core is ever going to use it because it's private. It does make the software easier. It means that the operating system can reschedule your thread on a different core, and it will just find all of that private data that you were using. At some point, I think we're definitely going to need to be able to put limits on that coherence, and also provide more explicit control over the vertical data motion through the hierarchy instead of having it handled transparently and automatically.
Okay, thanks. So this concludes the questions from the chat. I have a comment on your slide about the power cost of operating a system. So you assumed, first of all, you
Yes.
assumed 150 watts per socket, which is probably a little bit conservative, taking into account that
yes,
the most current chips have like 280 watts tops, right?
Right.
Even more when we look at Sapphire Rapids, for example. That's one thing. And second, that the price of electricity in the US, I'd like to contrast that with the price we pay here in Germany, which is, depending on the contract you have for a university, anywhere between 20 and 30 euro cents per kilowatt hour. So that's 30 plus US
20 to 30. Okay. I was curious about that. Our price at the University of Texas at Austin is actually lower than this number, but I didn't want to say it. Texas is an unusual place. On the other hand, we typically pay less than other people for the processors too. So it's a little hard to tell. One of the consequences here is that when people try to reduce the energy used by a program, and that's hard to do. You modify the program to reduce its energy usage, but they treat that as if it is an appropriate metric in itself. The more appropriate metric, I would say, is the cost, which is the sum of the depreciation or wall time used and the power used. And even at your prices, the wall power used is maybe 25 or 30% of the depreciation cost. You have to be very careful. Your reduction in power, your reduction in energy has to be a significantly larger fraction than any slight increase that you allow in execution time if you want to keep the overall cost lower.